6.13.1 Heat transfer and work in internally reversible steady-state flow processes. Previously, we considered the entropy balance for steady flow devices in the presence of irreversibilities. Consider an open system. So this red line is the control volume of the system. We are going to take the energy balance relation for the control volume. ds over dt. ds over dt is the rate of entropy change in the control volume. There may be heat transfer to the system. Q dot over T is the entropy change due to the heat transfer. T is the temperature where the heat transfer occurs. Mass flow going in and out of the system. Mass carries entropy. M dot S1 going into the control volume. M dot S2 leaving the control volume. And there may be entropy production in the control volume due to the irreversibilities. So we can put them together and write the energy balance equations. The small s is the specific entropy. The unit is kilojoule per kilogram times Kelvin. The large S is the total entropy. The unit is kilojoule per Kelvin. In this section, we are going to apply the entropy rate balance for steady flow devices without irreversibilities. We will also acquire the relations for the heat transfer and work from the entropy rate balance. Since it's a steady flow devices, time rate terms drops out. Assume it is an internally reversible process, so no entropy production. So the energy rate balance is reduced as this. The heat transfer per unit mass flowing through the control volume is temperature T times entropy change at the inlet and outlet. So in these expressions, we assumed the temperature at the boundary of the control volume where the heat transfer occurs is constant. The temperature is T. But if the temperature at the boundary varies with location, we can take integral of the temperature over the entire process. Do not assume that the entropy change of the system is zero. The system experiences heat and mass transfer. And recall that the entropy can be transferred by heat and mass. As heat is added to the system, entropy increases. As heat is rejected from the system, entropy decreases. See the TS diagram. The area under the process path is the amount of heat transfer per unit mass flow rate. The amount of heat transfer per unit mass flow rate for an internally reversible process. It is path dependent. Now let's see how the work can be expressed in the steady state single flow process. The energy balance equation can be written for a steady device with one inlet and one exit. Substitute the integral of TdS for Q dot divided by M dot. If we neglect the changes in the kinetic and potential energies, the equation is reduced. Using the second TDS equations, integral of t with respect to s can be written h2 minus h1 minus integral of v, specific volume, with respect to pressure. So plug this in to the equations. Enthalpy terms cancels out, and we also neglect the kinetic energy change, potential energy change. So W dot CV divided by M dot. For internally reversible process, the work is integral of V with respect to pressure. So on a PV diagram, this is the inlet 1, this is the exit 2. So the work, which is expressed as integral of V from 1 to 2 with respect to P, is represented as the shaded area. Work is path dependent. So the work may be related to the shaft work in pumps or compressor if the pressure increases during the process. Or it may be related to the shaft work in turbines if the pressure decreases during the process. Do not confuse the shaft work with the boundary work. The boundary work is expressed as the integral of P with respect to V.